Okay, welcome to the lecture 5 series, lecture 5 of the course Perception Algorithms for Autonomous Systems. In this course, we already have, first we started with primarily the introduction of autonomous system, then we discussed about what are the main course objective, that is direction, tracking and classification. We studied our we did our estimation theory. When we started tracking to or classification, we must have a basics of estimation theory. We started your least square approach, you started maximum likelihood, maximum a posteriori, and we called about Kalman filter. In last class, I have taken an vehicle collision avoidance example as well, which actually will signify the implementation of a first a alpha beta filter and then a Kalman filter. And what is the choice of Q and R, the two prime design parameter, that also we discussed. Now, we will be from the Kalman filter, now we will be little bit switching to the tracking part. Okay. We will be backing back to the Kalman filter, because tracking part, when we start, we need to do something called dynamics, tracking dynamics and the measurement models. Okay. So, what is called tracking first of all? Let us understand this. So, tracking means you want to compute the state trajectory or the trajectory of any vehicle or any system or any kind of object, okay, through your sensor. So, your sensors could be what? Your sensors could be radar, it could be any type of radar, pulse Doppler radar, FMCW radar, CW radar, plus passive radar also, not a problem. It could be your camera, it could be your electro-optic or IR sensor, it could be your LIDAR, it could be your ultrasonics. This could be anything. Okay. So, this is your measurement system. So, first because you know your state space equation. What state space equation says? X dot equal to Ax plus Bu and y equal to your h of x. So, if you have some noise, it will have W, it is actually V. Okay. So, this is your simple state space equation. What is state? You know, states are called the minimal number of systems behavior. The minimal number of system states are the kind of behavior which actually represent system dynamics quite well. Okay. So, that is your state, and states which are measurable is your actually measurement. So, you can write it that y, or you can write term it say z. Okay. So, now for the tracking, that object which you are tracking through your sensor has to have a dynamics, because object will move something. That is your actually that is called your state models. So, I want to capture the behavior of my dynamics. Okay. This is one. And with this dynamics, why it is important? Because when I will do, because this will be, I told in my last lecture, it has to follow a Markovian dynamics. In any state space equation, it has to follow a Markovian dynamics. So, this is your Markovian dynamics. That means, you know r at k minus 1, you want to go to time t equal to k. Okay. This is your dynamics model, and the same thing is the measurement model. So, this truth is actually something which you do not know, which you would like to estimate by using your tracking algorithms, Kalman filter, whatever you wish to use. You have only few sensor reports. So, you actually h of x k plus v k. So, this is actually your evidence that sensor is giving you. Okay. So, dynamics is important to go from current state to future state, and measurement is when you are doing a prediction, that prediction value will be updated by means of your measurement or correction. Okay. That is all Kalman filter we know. Now, target dynamics could be of different kind of a thing. So, before that I would like to do some brush up your linear control system theory course. In a linear control system theory course, we put continuous control, we put kind of studied the discrete control or digital control also. So, this is simply continuous to discrete equivalent. How from a continuous system you would like to go from a discrete this thing. Okay. So, this is say your continuous system, you have gone to the discrete. So, discrete how you go? In last my lecture of vehicle collision avoidance system, I did it. So, you can see this is state transition matrix, phi et is a state transition matrix, it is equal to e to the power a t. Now, you do a Taylor series linearization. So, you have I plus a t plus a square t square by factorial 2 plus some higher order term. So, I did it for till second order. Now, say I won't go for second order, I will go only for first order. So, I plus a t. So, lay my t is timestamp is very small, I can neglect my second order dynamics and all. Okay. There will be some error, but that is how it is. Okay. So, that is why I choose my timestamp or sampling time little bit lower value. So, that my higher order dynamics will not have any impact in my discrete equivalent. So, I can calculate. So, what is my continuous matrix into my sampling time plus identity matrix will give me my discrete equivalent state matrix or state transition matrix, number 1. Next thing, how my G I get. So, G is actually your B, discrete equivalent of your input matrix B. So, you can get it with the 0 to t phi tau b d tau. This is a simple formula. You can look into any digital control book either by Yogata, by BCQ or any book you can find, even Nagaraj Gopal also, any book you can find it out, any control system theory book you can find it out. Okay. So, G. Now, same thing you can now calculate your Wk. So, actually it will be phi tau b w tau into d tau. And when you do covariance matrix calculation, again it will be expectation of Wk transpose, and you can get this formula. Okay. So, 0 to t integration 0 to t state transition matrix continuous QC, QC is your continuous Q, this Q, continuous Q plus phi tau d tau. Now, how to calculate it? In when you are calculating Qk, I will tell you. Now, first you remember I started when the least square lecture. Least square lecture I purposefully took first order, second order, third order, 3 different dynamics. This is continuously, actually this is for tracking specific least square I have done. So, that is why you can directly now correlate why I have taken like this. When I say first order dynamics means it is a constant velocity model. So, first order means a linear model. So, x equal to a0 plus a1 into t. So, this is a linear model, a0 plus a1 into t. So, it means you have 2 state, your position velocity, you have 2 state position velocity. So, this is called constant velocity model. So, constant velocity means you do not have any acceleration. Okay, there could be something one model that is different, but actually you have 2 state x and x dot, x or vx, y or vy. If you do it 2 dimension, fine. Normally tracking, here we are considering tracking, I am not doing one dimension, I am doing it 2 dimension. So, say it is an aerospace vehicle, assume it is an aerospace vehicle, or even a ground vehicle also is fine, but let us assume it is an aerospace vehicle. So, you have x x dot, y dot, aerospace vehicle will have a z z dot as well, but I am assuming that z there is no motion, z is constant, it is maintaining its altitude. Okay. So, z axis I purposefully made it passive, but in practice it is not like that. If you are modeling in a aircraft or any missile, then you have z z dot higher derivatives of as well. Okay. With this, now this is called constant velocity model. This is very important. Even you are doing in a ground object tracking, even autonomous driver assistance systems or even in a mobile robot, you have to take up to this. You do not need z also. So, x dot, y dot. So, this is called your constant velocity model. So, in a constant velocity model, so you can see now when I go do the discretization, this is my continuous state matrix, this is my continuous input matrix, and with this if I do it, I get my this discrete with the same formula that earlier slide I have told, we get this is my discrete equivalent state transition matrix and this is my G2. So, for a 2 dimensional thing I have to for one for x, one for y. So, FCV model like this. So, it will be something like this 1 t 0 1, 1 t 0 1, here 0 2 cross 2, 0 2 cross 2. This is your state transition matrix, assuming I do not have any h. If the z is there, then there will be 1 0 0 0 0 0 0 and 0 0 0 0, so here 1 will come, that is all. Okay. So, this is my thing, and how I get my q, and the same integration that I have shown you here, with this I got my G matrix phi tau b d tau integration 0 to t. With this I get T2 by 2, T square by 2 into T. Now, there is a way how you can calculate your, there are two ways to calculate your covariance QK whatever. So, let us see or talk only about one axis only. So, this is your x axis, this is your y axis, this is your z axis anyway. So, let us see about x axis only. So, x axis G2 is there, it is direct equivalent to your 0 1, 0 1 t square by 2 t. Okay. Now, I am multiplying it like this, say t square by 2 in a column matrix and the transpose. So, this is a how much matrix? This is a 2 cross 1 matrix, this is 1 cross 2 matrix, 1 cancels out. So, it ultimately multiplication will be a 2 cross 2 matrix, you get this G transpose, okay. You get this thing obviously multiplied by your power spectral density of your Wx. Wx is your continuous noise. So, continuous noise means what is this PSD value, power spectral density value, say some sigma. This could be a tuning parameter ultimately, you will not be knowing this exactly, because this state is always your hypothesis, what you model it is yours, okay. You will not get any measurement or anything. So, like this. So, you can get your one dimensional x value, similarly the same thing will be your y, z is a passive axis. So, some small part variance value you have to give, okay. So, this is your CV model. Next thing, there is an alternate way of also doing things, okay. So, what I told, this is actually a constant velocity model. There is also another way to do it, that is called a Wiener process acceleration model, Wiener process velocity model. So, there actually what is a Wiener process? When we say Wiener process, that means actually x dot equal to white noise. So, that means delta x between two sampling instant is a white noise. So, in that case if you do, you get divided by t, some mathematical model equivalent, and you can get this kind of a equation of your QK. Now, if you put this equation with your phi is 1 t 0 1, your continuous is what 0 0 0 say PSD square. I am doing for one dimension, please remember, I am not doing for all the dimension. This is transpose d tau. If I do integrate, I will get this equation. Now, you see our previous equation and this equation, here this fellow is divided by a t, because this I have modeled it differently. I have modeled directly to the discrete equivalent I have modeled. In that case, previously it was a continuous, then I am discrete, and now here I have directly modeled it as a discrete target process. I can do anything, I can do continuous to discrete, I can do discrete directly, whichever way I can do. I wanted to do it in a Wiener sequence model. So, previously it was a Wiener process model, the last one, the last slide. Now, this is a Wiener sequence model, xk I directly model it xk minus 1 plus wk, the acceleration part, the v dot part, okay. The second state actually. If I do model it like this, I get this by delta t, both are okay, whichever way you find, it is fine, you can do this q value only divided by t. So, you get one order less. So, it will be t q by 3 t square, because all are divided by t, right, okay. This actually will be the fourth order. So, this is the difference, both are okay, again I am telling both designs are okay. This is you are going from continuous and then doing discretization. The other process you are directly working on discrete, you do not have this this thing, you have directly used it as a Wiener sequence. So, that is also fine for any models you can use in your tracking. Same thing for now, I will go for a, now suppose say my target is moving on a, I would say with a accelerated motion, with a constant acceleration, okay. So, I have my third order model, third order polynomial, second order polynomial, I have my second order polynomial. So, I have 3 states, my acceleration term will also come instead of velocity. Now, there are 2 ways to model it. One is called Singer's acceleration model, very important for a tracking point of view. What Singer does? Singer acceleration model uses first order Markov process, obviously 0 mean, with a autocorrelation this to model your acceleration, the forcing function. because it is a maneuver model. Maneuver model means there should be a forcing function. What could be? In a constant velocity pressure, it is the velocity. Now, here it is the acceleration. Okay. So, acceleration, if you remember your autocorrelation function, it will be AT into AT plus tau, assuming process is ergodic. You get sigma square into e to the power alpha into mod tau. Now, when you take there is something called Wiener-Kolmogorov process, you must have known any kind of your random process or random stochastic process, these books. If you do the Laplace transformation or Fourier transformation of your autocorrelation function, you get actually Fourier transformation, you get actually your power spectral density. So, once the power spectral density has come, that means your process is, suppose you are wanted to generate the thing, your input is a set of white noise and you are generating the AS. So, what is this transfer function? This transfer function is this. If you take your Laplace transform or even Fourier also is fine, I do not mind. So, if you take a Laplace transform, you get like this. Now, you take the stable part out, the stable poles out. You take the stable poles out, you get this. Now, you take the inverse Laplace, you get it like this. So, this is actually, this is similar to your state space equation, right, x dot equal to A x plus B u. So, something similar to like this. Okay. So, this is actually way your forcing function is modeled. Now, what is this alpha? Alpha is called correlation constant. Correlation constant means now if alpha is too large, that means you are taking a large maneuver, you are doing a turn. So, you are taking too much time to turn and alpha is very short means you are fast maneuver. When alpha is 0, A dot equal to W t. So, this is called a Wiener process model, again my old thing just I told, this is a Wiener process model. Okay. So, you can now when you do the discrete interpolation, the alpha will be e to the power alpha t. So, that is called beta. Okay. And this is like this. So, this is your discrete equivalent. So, just I am approaching this detailed modeling, so that at least you understand why this is important. Otherwise, you will be using only the final state transition matrix in your when you run your Kalman filter. Okay. So, with this now what you have done, we have done here, it is actually if you do your all this thing, you get simple sum this kind of a matrix after your this thing. Now, how to model the uniform distribution? So, you know, suppose Beckel, what is the max mean value of your acceleration? Suppose how much at max your Beckel can accelerate and what could the minimum value, and you can put a uniform distribution. This is the uniform distribution to calculate your variance, any variance. So, minimum max minus mean whole square divided by 12. This is your actually if it a uniform distribution give you the variance value. Okay. So, this is fine, I am just writing it here. So, with this now you go your this model. So, there are two again the same way as constant velocity, it is called Wiener process jerk model and Wiener process acceleration model. One is continuous to discrete equivalent, another one is direct discrete equivalent, same as velocity. You get this is your f, this is your q, like this. F anyway will be constant, but q value you can see the denominator thing is changing here, because it is just a way of modeling. It could be anything. It could be anything. Ultimately, this t value will be very less. What will be your t update rate? Say even 1 second. Okay. And but ultimately, it will be multiplied by something called PSD. Something called PSD. So, that will be, if you choose this, then this value actually will be negligible, but still it makes sense to kind of use the which kind of modeling you use. Both are right. You can use this, you can use this, does not matter. Okay. With this now, this much I have completed. So, with this it is a second order model. There is something called third order model also. So, you take jerk term and all, but this model size is kind of linearly increasing. There is no point to model such higher order dynamics, jerk and all. Although people have done it, but it is not very required. So, now something I will be telling is called kinematics modeling. So, what is kinematics modeling? There are two kinematics models are there, but I will tell only one, and the second one is bit complicated, I won't talk. So, this is called CSCT model, nearly constant turn rate, constant velocity model, or sometimes it is called coordinated turn model. From coordinated turn word has come from flight mechanics point of view, but it is actually a constant turn, constant bank to turn from that point of view. So, it is a constant turn rate, constant acceleration model. Okay. So, how these equations have come up, let me derive it here. Okay. So, suppose you are maneuvering, okay, target is maneuvering. By the way, all the CV model is only the non-maneuvering model. CA and this thing what I am now doing, CSCT, coordinated turn model, these are all maneuvering model. That you have to know both models, okay, for your tracking application. So, this is your say tangential velocity, okay. Normal component is anyway, there is no normal component. So, it is your tangential velocity. So, here is your heading. Say this is your y dot, this is your x dot. Sorry, my handwriting is not so good. This is actually your psi heading angle. So, your x dot will be equal to v of cos of psi, y dot will be v of sin of psi, right. Now, what will be? Now, take the double derivative, x double dot will be minus v of psi dot sin of psi, y double dot will be v of psi dot cos of psi. Psi dot means actually your rate I would say. So, if I term it as actually v of omega sin of psi. Now, v sin psi is equal to y dot. So, it is minus omega into y dot, and y double dot will be actually your omega into x, v cos psi is your x dot, your x dot. Okay. So, you now got two equations, x double dot equal to omega y dot, y double dot is equal to omega x dot. Now, you assume two things. Now, when you are doing maneuver, previously I have done it, acceleration is my maneuver function. So, I have done it, acceleration is my maneuver function. So, I modeled it as a Markov process and all this Signer model or something. Whichever I do not know, I have to model it some way. Okay. So, here is my omega is unknown. So, there will be certain, obviously to model my ignorance, this is my ignorance factor. I will model some white noise here, I will provide some white noise here, right. So, this is again I told, when I do not know something, I have to put some white noise, because omega is the forcing function. How I do not know how my target is maneuver or my vehicle has taken turn, I have no idea. I am sorry guys, I have no clue. So, I have to put some noise here. Okay. So, that is my ignorance about the real world, that is modeled using some random excitation, because I am telling repeatedly this thing because it will be helpful for you to kind of understand it physically. So, with this now if I go, this is my continuous model, x dot anyway you do not know, this is I got it, y dot. Omega is unknown, if omega is known, then there is it is a constant velocity model. Okay. So, you can do anything or not a constant velocity model, actually there is nothing, because because your job of your in a maneuvering target tracking is to estimate omega first, and then once the omega estimation is proper, your x, y, vx, vy estimation will be proper. Okay. So, now that is why your omega will be kind of a winner process. So, omega dot is equal to white noise. If you want to model it as a Markov process, well, your wish. Wt, sorry, this is omega, and this is W. Please do not, because both are same thing, you can use some other notation also, same, ultimately meaning will be same. Okay. So, here omega alpha is 0 means, alpha equal to 0 means actually you are modeling this as a winner process. So, that means the first maneuver, okay, does not matter. So, omega dot equal to some white noise. So, delta omega is unknown between two sampling instant, right. So, this is the way to design any unknown parameter. Here omega I do not know, I put it like this. In my last kinematics models, I did not know my acceleration, so I modeled it as a winner or Markov, whatever you say. That time when a constant velocity model, I was not sure my acceleration v dot, so that is why I put it v dot is equal to some white noise. Okay. So, this is very important. Forget this Markov, but at least this you should remember. It does not matter in tracking efficiency or tracking accuracy, but just way of modeling I use it. So, now this is a very important thing, you need to find it out. Here I am having a state omega I want to estimate, and the state omega is also there in my coefficient matrix. So, this model is nonlinear. Okay. So, this is actually my nonlinear. Okay. So, this model actually nonlinear. Previous models all are linear. If you see this 1 t square by 2. So, there is no component of state is there in your coefficient matrix. Okay. In the previous model 1 t 0 1, even whatever do this thing. So, there is nothing is there. Okay. But this model there is a omega term is there here. When the omega term is there and I am going the same e to the power a t I plus a t, this is going to be a non-linear model, because I am estimating omega, omega is unknown. So, this is a non-linear model. Okay. And obviously, when you simulate this model, your linear Kalman filter is not going to give you good result. So, you have to use some kind of non-linear filter. Okay. So, that I will be talking in next subsequent classes. So, this is actually your discrete equivalent model. Okay. And you use the same your this thing your same integration. So, you are actually phi tau QC phi tau transpose d tau. If you do, you get your QK. With this same, you actually get this is your Q matrix. So, actually same equation. Okay. Just a second, this equation. This integration, if you solve with this, you get this kind of nonlinear. So, Q is also now a function of omega. So, this is the thing. So, that means if you now you have to estimate omega each and every dt. If you estimate omega, then your this state model will be getting updated, or you do some integration, whatever you do. Ultimately, you have to get omega estimate in some means, because this state is going to this. So, now this is there is something. So, this is actually called a nonlinear model. So, it is understood. So, with this it looks very complex, very this thing, but it is actually a nonlinear. That is why it is so much this thing is there, and I wanted to show derive the actual thing. You can do it yourself by doing the integration, you will find it out. Okay. Just a integration, simple integration with a 0 to t. If you do this, you get this expression. Okay. So, this is the thing. Now, there are two things, very important thing that we should remember. So, this is called stochastic modeling. All I am talking about the target model, and next week next class I will talk about measurement model also. So, this is called stochastic modeling. In a stochastic modeling means there is certain call, because you have already done your deterministic models, you are clear, and those who have done this LQR or LQG and Kalman filter, this kind of course, LQG Kalman filter this course, they know some kind of stochastic modeling. So, stochastic modeling, the thing is that, so the main principle is that there will be some parameter which will be unknown, either in your coefficient matrix or in your forcing function x dot equal to ax plus bu. There should be some parameter which could be unknown in u, or which could be unknown in your a also. So, when any parameter or any physical coefficients in a, your system matrix is unknown, what you do? One approach is you model it and embed in your state. Your state dimension will increase, and how you model it? Model is same thing. If suppose A11 is unknown, so how you will model it? A11 dot is equal to white noise, or A11 k is equal to A11 k minus 1 plus Wk, right. You can model it like this way. Markup modeling is also okay. I do not care whichever way you model it. This is Wiener modeling. With Wiener modeling means with alpha is equal to 0. But you can do a Markup model also. It is your call. It is whatever you wish to do. It had nothing to do with your estimation in accuracy or accuracy. So, that is why whenever something is unknown, you have to model it using a stochastic Wiener process or Markup process. First order Markup only, not a second order. Second order also you can do it, but your state unnecessary to be complicated. Okay. So, this is one very important thing. And second thing, if your input function u is constant, then I am again repeating, you will give some, suppose when you incorporate your omega here, your omega is unknown. So, you given some kind of white noise excitation. Similarly, your x dot, because if you see this equation, I have put my omega y dot and this is an acceleration term x dot double dot y double dot. So, I gave my some white noise here y omega x and omega y just to model if I miss something. If it is not a proper coordinate turn model, then I am missing something, because truth could be what I do not know. I am enforcing this kinematics here, but it may not follow the kinematics. So, that uncertainty, so that ignorance is modeled using omega x, omega y. So, with this I would like to conclude the dynamic modeling or target modeling part. It is actually a stochastic modeling we talked, and thank you for your time. Next week we will be starting the measurement model, how to model my sensor, that part, that will be again important. Once that these two models are done, then we will be starting the target tracking. Okay? Thank you. Thanks for your time.